We were working in section 12.1 and 12.2 last time. And the last thing that we had done is that we had proved, or not proved, but we had constructed two congruent angles. We were given one angle, and we had created another angle congruent to it. And so our next construction is actually to combine that idea of constructing angles with the idea of constructing congruent segments to create a triangle. So we're going to construct a triangle congruent to another triangle given two sides and an included angle. So this is a side angle side postulate, okay? All right, so that's how we would have constructed our triangle given two sides and an included angle. Moving on, we're going to take a look at perpendicular bisectors. So there's two words here, and they're both going to be part of our definition. In order to be perpendicular, a perpendicular bisector, it has to be perpendicular, right? So it has to form these 90-degree angles. And bisector means that it cuts something in half. All right, so if we're wanting the perpendicular bisector of AB, it's got to cut AB in half, and when it cuts it in half, it's perpendicular to the line AB itself. You'll notice that every point on the perpendicular bisector, every point on this perpendicular bisector will actually be congruent from points A and B. Okay, so what do I mean by that? I mean that if you took that point that I just drew and you drew a line to A or you drew a line to B, they would be equal in length. And the reason is because if you see this right here, it actually created a triangle on both sides, right? They have the same base angle, 90-degree angle, they're right triangles. And they have a congruent side at the bottom that's marked here, and then they share the side in the middle. So it creates two triangles that are congruent, which means those lines that I just drew from A to this arbitrary point, we'll call it C up here, and the point from C to B, they have to also be congruent. So every point along that perpendicular bisector will be congruent on either side to the point A and to the point B. Isosceles triangles have base angles that are congruent. So isosceles triangles meant that they have two sides that are congruent, right? And that's the definition. But one of the properties of the isosceles triangle is that by having two sides congruent, it will automatically have two base angles congruent. And you can see that those are sort of shaded in, if you will, on A and C in the diagram. So if you start out with an isosceles triangle, meaning it has the two side lengths congruent, you automatically have the two base angles congruent. The angle bisector of the angle formed by the two congruent sides is the perpendicular bisector of the base. So this is a special, unique feature of isosceles triangles. It doesn't work for every triangle. But if your triangle is isosceles and you cut the angle in the non-congruent angle in half, it will automatically be a perpendicular bisector cutting the opposite side in half as well. Cool stuff, because that doesn't always happen. Okay, and the reason that's happening, if you want to talk about like, well, how do I know that that's the case? Well, the goal was we cut the angle in half, so we know that the angle is cut in half, correct? And we also have that the side here in the middle, this one is the same as the other one's side in the middle. They just share that side. And we know that these two pieces are the same. And if you're following it around, that's side angle side, right? Side angle side would make those two triangles the same, and if the two triangles are the same, then corresponding parts of congruent triangles are congruent. So that automatically makes these two base pieces the same length. It also makes this piece congruent to the other side, one side congruent to the other side. So why does that make them 90-degree angles? Well, we are trying to say it's perpendicular. So why is it perpendicular? Why does it create 90-degree angles? We know they're corresponding. I mean, we know they're congruent because they are corresponding parts of congruent triangles, right? They're corresponding, they're congruent. So why does the fact that they're congruent mean that they have to be 90 degrees in this diagram?
So they have to go to 180?
They have to add to 180. They're also supplementary, right? They lie on a line, so they're supplementary, they add to 180, and they're congruent. And the only two numbers that would do that would be the numbers 90 and 90, right? So if you've got 90 and you've got 90, they add to the 180, and they're also congruent to each other, so they would actually give you the 90-degree angles. So you do get a perpendicular to that side of your diagram. So this actually creates a perpendicular bisector. So it's perpendicular down here at the bottom, and it bisects the two sides. Okay? Typically speaking, angle bisectors and perpendicular bisectors are not the same thing, but in isosceles triangles, they are. Now, when you do actually create this perpendicular line from a point to the opposite side, that creates something called an altitude. I suspect you've heard that word before. We sometimes will call it the height of the triangle. Height just means the altitude. It's the perpendicular segment that goes from the top of the triangle to the opposite side. And it actually, every triangle has 3 altitudes, because you can do this from any angle. So I said the top of the triangle down, but you know that you can turn the triangle around on your piece of paper, right? So there's absolutely nothing special about me using the word top and the other side. It's any angle and the other side creates an altitude, and since there's 3 angles in a triangle, there will be 3 altitudes in a triangle, and they're all drawn in here. Now, the cool thing is they all cross in the center point. They cross in the same point. Okay? So that location actually crosses right there. Now, when they cross, we'll talk more about what that creates here. I think it's in another slide. Let's check it out. All right. I think it's further on. When you have a triangle, there is a way to create a circle around the triangle. There we go. And the circle that is around the triangle is called circumscribing. Okay, to circumscribe means to draw a circle around the triangle. And around the triangle means all the vertices of the triangle actually lie on the circle. So infinitely many circles would be around it. But to be circumscribing, it means all the vertices are actually on the circle itself. And there will be only one circle that will do that. Inscribed is how you would describe the triangle. The triangle is inscribed inside of the circle. The circle is circumscribing the triangle. And the circumcenter is the point where the perpendicular bisectors cross. That's the one I wanted a minute ago. The circumcenter. So over here where it said the triangle has 3 altitudes, the altitudes intersect in one point. That point is called the circumcenter. It's the location that tells you where the center would be so that you could draw such a circle. Okay? We will create a construction for this, but I don't think it's today. I could be wrong. But before this chapter's over, there is a construction for creating this circumcircle. So it's based on the fact that you're looking at perpendicular bisectors. All right. Oh, I was wrong. I was looking at 6 and it's actually 7. So we're going to create that circumscribing circle on number 7. But in order to do that, we actually have to know how to create perpendicular bisectors, which is number 6. Okay, everybody good? Okay. Okay, so reminder, that one might be worth rewatching because it is more complicated. It's the most complicated one, I think, of the 3, or of the 7, technically, that we've done so far. And the videos out there in Moodle Rooms. So if you go to our Moodle Rooms tab where you have all the other videos, there are videos separate for every single one of these. So it'll say video 7, constructing a circumscribing circle or something like that.
On the test, are you looking for us to know how to do all these separate things?
Yes.
Or, okay. I didn't
Yes.
know if it was like
So,
or if it was like know this to describe why.
It's a good question. So when you get to the test, there are 13 of these. When we get to the test, I will throw one of them out that you won't need to know how to do, and you guys as a class will get to select one that you throw out that you don't have to know how to do. So that will leave 11, and of the 11, there will be about 3 or 4 of them will show up on your test. And you will do a construction of the 3 or the 4 that are on there. Yeah. All right, couple more things before we get done. Example number 6. Consider a parallelogram along with one of its diagonals. Use the definition of parallelogram and the angle-side-angle congruence property for triangles to show that opposite sides of a parallelogram are congruent. Okay, so far we haven't actually defined a parallelogram in this way. We defined it as 2 pairs of parallel sides, right? But it is a true statement that the opposite sides of the parallelogram are congruent. And you probably remember using that fact at some point in your past to find like the area inside of it or something like that. Okay? So we're going to justify why that has to happen, and they actually give us a lot of information in this problem about how to justify it. They tell us that what do we have to create first? Triangles using what? The diagonal. We're going to draw one of the diagonals in, and not that it matters which diagonal that we draw, but it will help my description and your description to match if we pick the same one. So can we pick DB? Is that okay with you guys? Okay, so we're going to put in line segment from D to B to create two triangles, like Erica said. So now we have two triangles, right? Now in the triangles, all we know is parallel sides. We don't know anything about angle measures, and we don't know anything about side lengths. So you can't go through here and say, oh, these sides are congruent because the other sides are congruent. No, you don't know that. Okay, so you have to be careful to only use the information you really know at this point, which is stuff about parallel sides and the information about, what did I say? The parallel sides, we have it, and we have the diagonal length itself. So we do have one side congruent to itself, the diagonal, that part we have. Okay, we did some stuff with parallel sides, or parallel lines. So what were some of the things that we did with parallel lines that might be helpful here?
Interior angle.
We talked about interior angles, like alternate interior and alternate exterior, right? You guys remember that? Yeah, it's the interior angles that we're going to use here. So what I'd like for you to do first is consider, I don't care which we extend first, but let's just go with AD and BC as our parallel lines, okay? So I'm going to make them really long on my screen just to remind myself that these are actually lines that I'm talking about here. Okay, so, oops. Okay, I'm trying to move it over. There we go. There's my line as it's extended from D to A. And then I'm going to have another line over here from C to B. Okay, so these are parallel lines, correct? What would we call the red line in relationship to the yellow lines? Transversal. So this is a transversal of those two lines. So anything that we talk about in terms of angles needs to be measuring from the red to the yellow. Okay, that's all we can measure. So in particular, we want to measure from red to yellow, but we kind of like to be inside the diagram. And in particular, we kind of like to be inside the separate triangles. So one of the angles that's really helpful to talk about, we'll do it this way, is this one. So if you're thinking about parallel sides, yellow, the two yellow ones, which other angle, we'll just give it a name visually. Visually, where is the other angle that's congruent to my pink one? Yeah, this bottom one right here, right? These two are alternate interior angles, agreed? Yes. So we're going to write that down. So we've got our two angles. Angle ADB is congruent to angle DBC. And when we write down that that's a fact, we need to justify why. And the reason why is because these are alternate interior angles for which set of parallel lines? AD. So segment AD, or you can even put line if you prefer here, either way, being parallel to line BC. Those are alternate interior angles for that pair of lines. Okay, everybody good so far? That's one angle. We're supposed to be using angle, side, angle. That's one pair of angles. You know the side. What side are we going to have? The one that I drew in red, right? So we can actually write that down too, because that's the segment we're going to need. It's DB. DB, segment DB, make sure you're putting segment, is congruent to segment DB. Why? They're the same line, and they're actually, if you write same line, I'm okay with that. But there is a name for it, I'll tell you. It's called the reflexive property. Okay? Like a reflection in a mirror, the idea. It's a reflexive property. Okay, I'm going to erase my yellow lines now because they're not real helpful for me at the moment, and the pink angle. I already know the pink angle is congruent, but I don't need it at the moment. I still need my red line in there, so I'm going to leave it. All right, so this is what I have now. Everybody good so far? The other set of parallel lines will give me the other angle that I need. So we're going to draw in DC and AB. Okay, so we still have the red transversal. You have to sort of forget the yellow lines in your mind for a minute. It's a little bit hard sometimes to look at it in a different perspective, but you can do it. I need angles that are inside the triangles that are trapped between the red line, or the red segment, and the purple now. So what angle am I going to be using? ABD, this one right here. It is one of the angles in the triangle, and it is trapped between the red transversal and the purple. And its alternate interior angle would be which one? Yeah, I covered up my letters, but it's this one right here, right? CDB, I think. Is that how it's labeled? Okay. And they're congruent because they're alternate interior angles of parallel lines, right? So let's write those down. So now I've got angle ABD congruent to angle CDB. And again, the reason is because alternate interior angles for the lines AB and DC.
Do we say and or parallel, or either?
It would be better if I said parallel. I will fix that. I like that much better, yes. If you didn't say it, I think you'd still be okay with me, because otherwise you wouldn't have alternate interior. It wouldn't make sense to talk about it in terms of anything else besides parallel lines. So if you did forget that fact, you'll be all right.
I just asked because you put parallel on the first one.
Yes, it didn't match. You're right. The structure was not the same. Okay, so we now have, in terms of my picture, we're not quite there because we haven't actually proven anything yet about the side lengths, which is what the whole point was. Let me draw my red line in again. Got this one. I've got the blue angles here that are congruent, and I had the pink angles that were congruent. So I contend that my triangles are now congruent. Why? Yeah, angle, side, angle. So, okay, that didn't work quite well. Let's try again. All right, so now triangle ABD is congruent to triangle what? Got to have it in the same order. So which angle is congruent, do you believe, to A? C. Which angle is congruent to the, which one was it? B. The blue angle B. Yeah, the blue angle D. And then the other one's B down here. So CBD. And what's the reason? Why do I know this to be true? CP, CTC, corresponding parts of, actually that's not right. That's what I need in a minute. I'm sorry, I jumped the gun. Angle, side, angle is what I need first. By angle, side, angle. And then I have my sides. So now AD is, oops, I had that right first, is congruent to CB. And AB is congruent to DC. And the reason for this is that corresponding parts of congruent triangles are congruent. All right, so this leads us into the last piece of information. The last piece of information references a slide sheet, a separate sheet that I actually have out there. Did everybody print these out when you printed your notes? Fantastic. We're not going to go over this in depth, but these are facts that can all be proven about these different shapes. when you get to the point where we're ready to take a chapter 12 test, these facts would be helpful to know on a lot of them, okay? But we're not going to prove all of them. We will prove some of them throughout. We've already proven one. For parallelogram, we proved that the opposite sides are congruent. Opposite angles are also congruent. We could actually prove that with the same argument that we just created. Corresponding parts of congruent triangles are congruent. We could create the corresponding angles, right? The diagonals bisect each other. The quadrilaterals, all this stuff. These are all things on the side where it says related theorems that can actually be proven using the definitions and mostly triangle properties, actually, like triangle congruences. So you have this as a reference as you're working through your other things, okay?